Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a simple tutorial on hyperspectral image classification using SVM or support vector machine. Let's get started. As I said in this video, I want to talk about hyperspectral image classification using SVM. Let's first briefly talk about SVM and what it is. I'm not going to go in depth though. If you want a more in-depth video on the basics of SVM, just go to one of my former videos on my channel, which is shown right here. SVM offers a very high accuracy compared to other classifiers such as logistic regression, decision trees, and so on. It is known for its kernel trick to handle nonlinear input spaces. The classifier separates data points using a hyperplane with the largest amount of margin. SVM finds an optimal hyperplane which helps classify new data points. Some problems can't be solved using a linear hyperplane as shown here, left-hand side, this figure here. In such situations, SVM uses a kernel trick to transform the input space to a higher dimensional space as shown on the right. The data points are plotted on the x-axis and z-axis. Z is the squared sum of both x and y. Now you can easily segregate these points using linear separation. Kernel tricks helps you build a more accurate classifier. In this video, I want to show you how you can apply SVM for hyperspectral image classification. The dataset that I'm going to use is Indian Pines dataset. The Indian Pines dataset is a widely used benchmark dataset in the field of remote sensing and hyperspectral image analysis. It was collected by the Indian Pines Research Project, hence the name. The dataset consists of a hyperspectral image captured by an airborne sensor over an agricultural area in northwest Indiana. The dataset contains 224 spectral bands or channels, and the wavelength range typically covers approximately 400 to 2500 nanometers. I have written two scripts for this work. In the first one, I use 20% of the data randomly chosen as testing and the rest as training. At the end, I will also report the confusion matrix and the accuracy of the SVM classification results. In the second script, I will run the first code 5 times in a loop. That way, I would be able to get the results of the classification for the entire image. 20% of data for testing each time run 5 times, which would enable me to do the classification on the whole image, as shown here. This would enable me to present the results of the classification for the whole image as well, and compare the results visually with the ground truth. So as you can see here, each time 20%, 5 times, and I would be able to get the result for the whole image. Okay, let's go to Python and show you the code. Okay, here's the first script. These are the libraries that we need, and this is where our data is located. And I'm going to be loading the data here, and I'm going to reshape them here. Y here is the ground truth. That's why it only has one channel. And X is the hyperspectral data, and it has 220 bands or channels. I'm going to apply PCA to the data. This is also where I plot the cumulative explained variance, which also helps me determine the number of principal components I need to retain most of the variability in my data. And then this is where I'm going to be visualizing the first 8 principal components. And this is where I'm going to be splitting the data. 20% of data is going to be using as testing, and that 20% is going to be randomly chosen. This is where I'm again applying PCA to the data, but the number of principal components are going to be 100. Applying PCA to your hyperspectral data makes the training much easier, because there's a lot of data in your hyperspectral image, and when you use the whole bands, it's going to be hard for the system to learn the pattern. So we apply the principal components to make it easier for the system to learn the patterns in your hyperspectral data. And the system here is SVM. This is where I'm going to be applying a nonlinear kernel. I wrote linear, let me change it, this is nonlinear. And now this is where I'm going to be fitting the data to my SVM model. And this is where the testing data is going to be used to predict their output using the SVM model. But again, before that, we're going to apply PCA to the testing data as well. But notice that I'm using the same principal components as in my training data sets, because everything that is applied in your testing data, it should come from your training data. And you can see that I'm not extracting the principal components from my testing data, but I'm extracting them from my training data. But I apply the same principal components to my testing data. Because in machine learning, it's very important not to use your testing data for any training purposes, and only the training data should be used for that. So as you can see here, I'm extracting the principal components from my training data, and I'm compressing my testing data using the principal components that I extracted from my training data. Anyway, this is where the output for the testing data is predicted, and I'm going to show you guys the confusion matrix here, and I'm going to plot the confusion matrix, and I'm going to report to you guys the accuracy. Let's run this script and see what happens. As you can see, this plot shows the cumulative explained variance. And to retain the variability in our original data, we need to have enough principal components. And in this work, we use 100, and as you can see, we get enough variability back from our original data. As you go to higher principal components, like principal component 200 or 180, you get more noise in data. And this is our confusion matrix, and the average accuracy is 0.68, which is not bad. Especially considering that we don't have too much data, the model has not done a bad job. And I'm pretty sure if you play with the model with other kernels, you might get a better result. But for the sake of this video, this suffices. Now, for me to be able to show the result of classification for whole image, I have to run the same script 5 times. And each time, I'm going to be using 20% of the image as testing. That way, I could compare the model's output with the ground truth. All of this is going to be done in the second script. Okay, let's go to the second script. This is almost the same as the first one, but in this one we split the hyperspectral image into 5 parts, and then we use one part as testing and the other 4 as training, and then we loop through the 5 parts to have the result of classification for the whole image, as I explained before. Okay, first we import the necessary libraries. This is where the data is located. This is where we are loading the data. And this is where we are reshaping the data first. Y is the ground truth and X is the hyperspectral data. And this is the loop that I told you about. It's going to have 5 iterations, and then I'm going to be saving the whole accuracy and also the whole classification result. So this is how I'm going to be splitting the data into 5 parts. As soon as we come into the for loops, we specify first the indices for the test and training samples. And this is where we specify the data. We apply the PCA to the data to only use the first 100 components. And this is where the nonlinear SVM is applied. And this is where the SVM is fed to the training data. And then this is where the predictions are made on the testing data. And then I'm going to be calculating the accuracy. And then I'm going to save the accuracy for all the 5 iterations. And then when we come out of the for loop, the first thing we do is to calculate the accuracy for all the iterations, the average accuracy. This is where we show it. And this variable has the classification result for the whole image. And this is where we're reshaping it, and this is where we're showing it. And then we compare it to the ground truth. So that's it. Let's run it, see what happens. It's going to take a little while because it's going to go through 5 iterations, and in each iteration, one part is going to be set as testing and the other 4 is going to be set as training. This way of running has enabled us to compare our classification result to the whole ground truth. Okay, the run is complete. As you can see, the accuracy is 0.69. This is the average accuracy of the 5 runs. Let's go up. This is the accuracy from the first script, and this is the overall accuracy of the 5 runs, and it's 0.69, which is almost the same as the first script. And this is the classification result of the whole image as opposed to the ground truth. You see that we have not done a bad job, and it's almost the same accuracy as the first script. I'm pretty sure if you play with the model or have more data, you're going to get to a better accuracy. But for the sake of this video, this accuracy suffices. And you could also access these scripts using the link in the description section of the video. And that's about it.
Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.